Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we were talking about the thin walled pressure vessel, that is and we found out the force developed in that thin walled pressure vessel, as well as we have found out the radial expansion due to the application of the internal all round internal uniform pressure. Okay. And then we talked about the mechanism of the belt around a wheel. So, when the wheel is not frictionless. So, there we found out the tangential force developed at one point of belt will not be same at the other points. So, because of your friction, it will be that force will be increasing in the exponential order. Okay. Now, we will be taking couple of numerical problems. So, first problem, it says a triangular frame supporting a load 20 kilonewton is shown in figure. So, I will show the figure later on. Determine the displacement at the point D due to the 20 kilonewton load carried by chain hoist. Okay. The problem says, so this is the figure. Okay. So, the problem says a triangular frame supporting a load, this triangular frame is this. So, BCD okay, is supporting a load of 20 kilonewton as shown in the figure. So, determine the displacement at the point D. Okay. So, this displacement of point D due to the 20 kilonewton load carried by the chain hoist. So, this is the chain hoist, because of that you need to find out the displacement of D, okay, where it is given the cross sectional area of CD equal to 3200 millimeter square, cross sectional area of BD is equal to 491 millimeter square, and the modulus of elasticity of both the members are made of same material. So, E is given as 205 into 10 to the power 6 kilonewton per meter square. Okay. So, before going to find out the geometric compatibility and all, what is your first step? First step is to study the forces, right, by exploiting or by satisfying the equilibrium conditions. Okay. So, let us draw the free body diagram of this, okay, of this frame. So, the free body diagram will look like this. This is point C, you will be having the force Fc from the support. This is point D, this is point B. So, similar kind of problem already we have solved earlier. So, you will be having the reactions F B Y, F B X, and this will be the resultant F B. Okay. Now, again for the sake of completeness, I can ask you that why I have considered, or we can discuss this thing, that why we have considered F C in the horizontal direction and F B along the member B D. So, these things already should be known to you. Already we have discussed this thing earlier when we are discussing similar kind of problem, okay, when we are talking about the, I mean, when we are discussing or when we are determining the support reactions. Anyway, so now basically what we are going to do, we are going to find out the support reactions, because without knowing the support reactions basically you cannot proceed. So, that is why the free body diagram has been drawn, and then support from the support reactions, basically once you know the support reactions, then you can consider different joints and you can find out the member force. So, once you know the member force, then only you will be able to find out the geometric deformation, right. The second step is the study of deformation, is not it. So, first step is the study of forces. So, now we are studying the forces. So, deformation will be coming later on when you know the forces are acting on different members. Okay. So, now considering the equilibrium, that is we are considering moment equilibrium, that is summation of moment with respect to point C is 0. So, what we can write, Fbx into 3, okay, minus 20 into 3 is 0. So, from that we can get Fbx equal to 20 kilonewton, fine. Similarly, we can exploit this condition, summation of Fx, where you can think of this is my xy direction, okay, summation of Fx equal to 0. So, I can simply write Fc minus Fbx equal to 0. So, from which I can get Fc equal to Fbx equal to 20 kilonewton. Okay. Similarly, I can exploit this condition as well, summation of Fy equal to 0, from which I can get Fby. What are the forces acting in y direction? Fby and 20 kilonewton. Okay. So, Fby will be simply 20 kilonewton. So, therefore, we can get Fb equal to root over Fbx square plus Fby square. Similar thing we have already done for earlier in the lecture. So, that will be giving me 28.3 kilonewton. Okay. So, now we will try to find out the forces in each member. So, what are the members? do exist in the problem, member BD and member CD. So, we need to find out the forces carried by each member of the frame. Okay. Now, we know the support reactions, that means FB and FC both are known to me. Now, if we consider each joint, so joint C if we consider, or if I consider joint B, I can find out the member force in CD and BD. Okay. So, let us do that. So, we are considering, so force, now we are talking about, now still we are studying the forces, say we are trying to find out the member forces. So, this is my member CD, and we are considering the member force in CD is compressive in nature. I told you several times, I am telling this thing that you need not to think about whether it should be compressive or tensile. Right now, I am considering compressive, that does not mean that I know the answer, that is why I am writing. Okay. So, you can take tension, if it is really tension, then it will be becoming positive, if it is not really tension, then it will be becoming negative. Now, for example, if I consider compression, okay, and if I get positive value of FCD, then it is really compressive. If it is not really compressive, then it will be becoming negative. So, this thing, several times I am saying you. So, you need not to think much about these things, the direction of the force. Well, and I am considering BD, say tensile. Okay. So, I am considering BD as BD is under tension, that is FBD is tensile in nature and FCD is compressive in compression force. Okay. So, now you need to find out the force FCD and FBD, FCD and FBD. Do you know the magnitude numerical value of these forces? Yes, you know. How do you know? If you consider the individual joint. So, suppose I am considering joint C, this is my joint C, this is FC, okay. This is FC and this will be FCD. So, FCD is nothing but FC. Agreed? So, therefore, whatever direction we consider, that is compressive force, FCD is compression in nature, then that comes perfectly fine. Okay? So, FCD is equal to FC. So, I can write FCD equal to, FCD was 20 kilometer. So, this is 20 kilometer. Now, what about FBD? So, you consider joint B. So, this is your joint B. Okay. So, from joint B you are having FB. So, this is the vertical direction, this is the horizontal direction, okay, and this is your FBD, right. So, from this, from the equilibrium of joint B, you can simply say FBD is nothing but equal to FB. So, FB already you have calculated. So, FBD will be, FB is nothing but 28.3 kilometer. So, my study on the forces is over. So, I have got the information about the support reactions, and from the support reactions I have got the information about the member forces, right. So, the study of forces is all over. Now, we will be studying the deformation. Now, if you look at this member CD, and I am saying that member CD as well as member BD both are deformable bodies, right. I am not talking about a rigid body or something like that, they are deformable bodies. Now, under this action of force FCD, the member CD will be compressed. Now, what will be the amount of compression? That we can calculate by using your Hooke's law, PL by AE, right. Similarly, if you consider member BD under the action of this tensile force FBD, that member BD will be elongated. How much will be the elongation? That also we can calculate by using the simple Hooke's law. So, let us calculate those things, okay, and let us get the numerical values. So, your delta BD, so delta BD is the expansion or the elongation of the member BD, because that BD member is under tension. Okay. So, that is given by FBD, length of BD member, cross sectional area of BD member, and EBD. Okay. So, you put the numerical values here. FBD is 28.3 into LBD, you can calculate 4.242 into 10 to the power 3 by area is given 491 into 10 to the power minus 6 into E is given 205 into 10 to the power 6. Okay, fine. So, from this you can get the value will be coming as, if you calculate the value, it will be coming as 1.19 millimeter. Similarly, you can calculate F delta CD, which will be compressive, which will be the shortening of the member CD. Okay. So, that is FCD, LCD, ACD, ECD. So, if you put all the values, you will be getting 0.0915 millimeter. This is, you can write extension, and this is compression. Okay. Now, whatever values you are getting, what it will indicate? That means, if you do not have the frame, suppose you have individual member BD and CD under the forces FBD and FCD respectively, then member BD will be extended or will be elongated by this much amount, and member CD will be compressed by this much amount, if I do not consider any assembly. But when they are actually connected or when they are present in an assembly, then basically they, I mean these values have to be satisfied, but at the same time they cannot behave individually. What I mean to say, the joint, suppose if I consider the elongation of BD, the BD will be elongated like that and CD will be compressed like that, then where is the point D? So, now CD after compression D point will be coming here, and after elongation of BD D point will be coming here. That is not acceptable, because they are acting in an assembly. So, the D point will be the common point even after deformation. Before deformation, D point was the common point where CD member and BD member, both members are meeting. Even after deformation, D point will be the common point for both the members, but at the same time they have to experience this much of deformation. Now, how to do that? Okay. So, let us draw the geometric compatibility figure, okay, and then I will explain. Let me draw it. Okay. Now, let us understand this figure first. As I told you that if BD and CD are not in the assembly, okay, so this BD is free to elongate up to BD1, agreed. If what I said, if BD and CD are not making this frame, or they are free to expand, or they are free to deform, then BD, due to the action of FBD, that is the member force, BD will be elongated up to BD1. So, this from D to D1 distance is nothing but the elongation delta BD, whatever we have calculated, fine. Similarly, if CD is not in the assembly, if CD is free to deform, then this CD will be compressed, okay, under the action of FCD, and it will take the position of D2 CD2. So, D will be shifted to D2. So, now CD2 is the compressed member if we are allowing free deformation of the members, right. So, D2 is nothing but your delta CD, agreed. So, what, and for example, I mean for the sake of completeness, we must think that this problem we are defining with small deformation problem. If we consider the same problem with large deformation problem, the formulation and analysis will be completely different. But so far, as I told you, in this particular course we are not talking about, or we are not concerned for the large deformation problem. We will be only restricting ourselves to the small deformation problem. So, if it is the small deformation problem, so, and the figures of course it is a little bit exaggerated figure to understand in a better way. Okay. So, this DD2 is your delta CD and DD1 is your delta BD. So, basically BD will be taking the point D1 and CD will be taking the point D2 if they are free to expand or compress, but that is not happening because D point is the common point. So, I cannot have some different point D1 and D2. So, they should be in the same point. So, what is happening then? D, if you consider, D will be taking the arc kind of thing. So, D point, this is the common point for BD and CD, this point will be becoming D prime point, where this BD is getting expanded and CD is getting compressed. Okay. Though these angles and all those things are not looking like the same angle, but for the small deformation problem, and as I told you this is a very exaggerated figure, but those angles will be remaining same anyway. Now, how to get this D prime point? Now, what we are doing here, from this point D1 we are drawing one normal to line BD, or the BD1 rather, we are dropping one normal to this. That line is coming like this, okay. And from this CD, from point D2 we are dropping another perpendicular line. So, these two perpendicular lines are meeting with a common point D prime, okay. So, frankly speaking, that should happen through the I mean circular arc, but nevertheless if we consider like this, dropping the normal, that will be also fine. I mean that will not create any significant difference because we are dealing with the small deformation problem. So, what we did, we draw a normal line or the perpendicular line from D1 and another perpendicular line from D2, which will be meeting a common point D prime, okay. Now, this D prime is the final point after deformation. Before deformation it was at D, now after deformation it is becoming D prime. So, what is the displacement of point D? So, D is coming to D prime. So, this much is your horizontal displacement or the horizontal shift of point D, and D is coming to D prime. So, therefore, this is your vertical displacement of point D, fine. Okay. So, if it is so, then from the figure it is very clear that delta DH, that means the horizontal displacement or horizontal shift of point D is equal to delta CD. You just look at this figure, is equal to delta CD is nothing but 0.0915 millimeter. Okay. And what about your delta dV, that means the vertical displacement of point D, that will be, if you look at figure, d2f plus f d prime. So, d2f plus f d prime. It can be further written as d2f is nothing but d2 as dg, you look at here dg, this dashed line or the dotted line, plus f d prime. Now, this dg can be written in terms of delta bd in this fashion. So, delta bd by cos 45 degree plus. Now, what is f d prime? What is f d prime? So, f d prime is nothing but your f g, because this angle is 45 degree, right. So, if this angle is 45 degree, so f d prime is nothing but equal to f g. Now, what is f g? F g is nothing but equal to delta c d. So, I can simply write delta c d. So, by putting the values here, you know delta b d, you know delta c d, the numerical values. By putting the values here, you will be getting 1.77 millimeter. So, what did you get? You got the horizontal displacement or the horizontal shift of point D is this much, and the vertical shift of point D is this much. Okay. So, this is the way you solve the geometric I mean, basically this figure is coming from your geometric fit or the geometric compatibility, because D point cannot be different. So, you cannot have D1, D2 two different points after deformation, it will be the same common point. So, D has to take the position of D prime. Well, so I will stop here today. In the next class, we will take another numerical problem and then we will move to the next topic. Thank you very much.